Good morning and good afternoon. Thank you for attending the CXL Link Level Integrity and Data Encryption webinar. Today's webinar will be led by Raghu Makaram, Principal Engineer at Intel Corporation, and David Harriman, Senior Principal Engineer at Intel Corporation. Now I will hand it off to Raghu to begin the webinar.
Thank you, Kausa. Good morning, good afternoon. So CXL is a coherent, low latency, high bandwidth interconnect. This is used to connect CPUs, GPUs, accelerators, and memory. In these usage models, high value data moves across the link. So it's essential to secure this data as it moves across the link. CXL integrity and data encryption, the CXL IDE, provides such protection. So today we'll explore CXL IDE in detail. We'll start with a discussion on what the threat model is that we are looking at and how IDE addresses these threats. We'll follow this with, how you know who is on the other side, this device at the station and key exchange so that the keys that are needed for IDE are established. And then we'll dig deeper into how CXL IDE is implemented, both at the CXL IO protocol and for the CXL.cache protocols. And then we'll conclude by looking at the error handling implications. Let's dig right in. Okay, from a threat model perspective, the data we want to protect, right, is the protocol transactions that are going across the link. So if you look at the diagram on the right, it shows an example system with a host that's connected to a CXL endpoint. Maybe there's a switch in the path, and there could be, multiple endpoints connected below the switch. The primary asset that you want to protect is the data, right? Both the, protocol transactions and the data and header that goes across the link. And of course, any cryptographic keys that are involved in setting up and using the IDE would also require protection. In terms of adversaries, we focus on kind of the physical adversaries, right? These are skilled or simple hardware adversaries who can snoop the data going on the link or modify it, inject, collect data and replay it at a later point in time. There's also other things like, swapping out a device or removing a device. While the threat model, right, the IDE is designed based on the physical adversaries as sort of the benchmark for designing the IDE, IDE itself is a foundational building block for other types of threats. This could be, untrusted software or network adversaries. In these cases, right, IDE becomes a valuable building block, a tool that can be used to secure systems, for example, if you're trying to build confidential computing systems. Now, a TCB or trusted computing base sort of defines the set of things that you must trust in order for the IDE to work properly. Clearly, the implementation of IDE in the root port and in the endpoints would be within the TCB. Now, the agents that configure these endpoints and IDE would also be part of the trust boundary because they are the ones that are configuring these keys. Now, the switches bring up an interesting case. As shown in the diagram on the right, you see that the CXL.cache IDE sort of terminates at the switch port, and then a new session is set up between the switch and the endpoint. We will talk more about what this means and how switches get used later. But from a CXL.cache IDE perspective, the switches would be the TCB. When physical adversaries are in scope, denial of service is something they could easily do, right? Just unplug the device and you have a denial of service. So defense against such denial of service attacks is not in the scope for IDE. Let's look a little bit about what the protocol stack is that's used to kind of know who is on the other side, attest to their goodness, and perform key exchange. the device, all of these messages for enumerating the device or attesting to the device flow over CXL IO protocol. And the both CXL PCIe IDE ECM that's used on the CXL IO side and CXL IDE establishment ECM describe sort of the mechanisms that are used. These sort of build on the DMTF SPDM or security protocol and data model specification. So SPDM defines this method for exchanging messages securely over an SPDM session. PCIe established a mechanism called secure object exchange, which is really a sort of mailbox registers on the endpoint. And these can be used in a secure way to send secure SPDM messages. And the CXL IDE, both on the IO side and cache-mem side, would leverage these DOE mailboxes. There are other mechanisms, like an alternate path that's available through SPDM, use like an MCTP binding or use NSM bus. These alternate mechanisms are available for, these are defined by DMTF and specific usage. Users can leverage these alternate mechanisms as well. The device attestation, like I said before, we start by building on top of PCIe and SPDM specifications. And this starts with what I call a hello message, right? Really, getting to know who's on the other side, sort of understanding their capabilities, negotiating algorithms. That would be later used to do other things. So at this point, you sort of know who's, what the other person is capable of, and then you kind of get who's on the other side by a get certificate call that returns a certificate, which has really the devices or the endpoints unique identity. This is sort of who the responder claims to be. Like, this is my certificate, this is who I am. To confirm the identity of the responder, like really, are you surely who you are? There's a challenge response protocol that's built where the requester sends a challenge and the responder, signs the challenge to prove that they are indeed the owner of the private key that's associated with the certificate. So at the end of this challenge response, both sides know who's on the other side. And now, if there's additional information to be had, things that could be more dynamic, things like configuration information or firmware revisions that are used, those could be obtained by using the measurements, get measurements protocol. So with that basis of knowing who's on the other side, the IDE establishment, key establishment builds on top of that. The first step in that is to a key exchange to set up a secure session, the secure SPDM session between the request and responder. Once this key establishment is done and the secure session is set up, it can then be used to transport additional information between the two sides, right? And this could just be things that just need authentication, or things that need both encryption and authentication. These, for the IDE key establishment, of course, the IDE keys themselves are secret, so these would be encrypted and integrity protected and sent across a secure session. The secure session itself has a notion of heartbeat to keep it alive, and then periodically the secure session can be updated. Of course, the secure session, once it's kept alive, could also be used to update the IDE keys, like refresh the IDE keys periodically. Let's now look at, we talked about how keys are established, but what are these keys used for? What are the properties of IDE? CXL IO IDE follows the PCIe IDE snap. CXL.cache and IDE is defined in CXL spec. There's a lot of commonalities between these two. Both of them use AES TCM with 256-bit keys for data encryption and integrity. So this is how the protocol data is protected. And there's a part of the ESDCM is this integrity value that gets transmitted, and this is a 96-bit MAC that's transferred or transmitted for integrity protection. And these are the keys, right? The ESDCM, there's 256 keys are the ones that were exchanged previously. We talked about the key exchange protocol. Now, both CXL IDE and CXL CacheMem really protect the protocol switch, right? And anything that is more control, control messages or control information, things like DLLP, sequence numbers, or link CRC in the case of CXL IO, or control flits or link CRC in case of CXL CacheMem protocol are not protected by IDE. These sort of flow independent of the IDE. So these are sort of some common things between the two. There's another commonality, right? Both CXL IO IDE and CXL CacheMem IDE have the ability to provide additional robustness against crypto engine errors, right? Things like hard or soft errors in crypto engines are protected by an encrypted plaintext CRC. We'll talk more about what this means and how this is done later in the presentation. Now let's talk a little bit about differences between the two. CXL IO IDE has sort of these two variants, right? A link IDE and a selective streams IDE. Link IDE protects all the protocol traffic that goes across the link. Whereas a selective streams IDE is more selective. It can protect a subset of the data or a subset of the protocol traffic that's going on the link. It could just be an assignable device interface like a password, or maybe it's a device function that's targeting a given endpoint, and only that component is protected by the IDE. The selective streams IDE kind of allows an ability for the switches now to be configured in what's called flow-through mode. In this case, the switches don't need to implement the full IDE protection. Of course, they need to do certain things like making sure all the ordering rules are maintained within a stream, but they don't need to implement the cryptography involved in IDE. And this sort of selective stream could then be between the root port and endpoint, kind of passing through the switch. So now you look at CXL CacheMem IDE. CXL CacheMem has only link IDE, as well as notion of selective streams. And in the case of CacheMem IDE, the unit of protection is a protocol flit. So the entire flit is protected by IDE. There's 32 bits of flit header that's only integrity protected but not encrypted, and the rest of the flit header and all of the data in the all data flit is encrypted and integrity protected. So in case of CXL CacheMem IDE, only the switch must support link IDE because that's the only thing we support in CXL CacheMem, and this is a very deliberate choice. Right? CXL flits, if you think about, pack a lot of information. There's opcodes and data, and these could be, multiple of these are packed in one flit, and each one could be targeting a different endpoint. And from a switch that implements CXL CacheMem protocol, it really needs to look deep into this flit, unpack the flit, unpack and understand the opcodes and data involved, and then repack it before forwarding that. So that's like an IDE flit can just be transparently switched. So the CXL CacheMem IDE, if there's a switch in the path, it has to implement the link IDE. So now let's go further and understand more details about and explore CXL CacheMem IDE. CXL CacheMem IDE requires a couple of minor protocol enhancements to enable the use of IDE. There are two parts. One is a new header slot. Right? This is a slot to carry the MAC information, and header slots normally carry 96 bits of information. So this 6 header slot, all of the information in the slot is MAC. So 96 bits of MAC is transported. The IDE also introduces a new control flit, and this IDE control flit has sort of 3 sub messages, and let's kind of walk through this. The IDE TMAG, right, the truncated MAC, is a way to kind of terminate a MAC epoch early. So what's a MAC epoch? What does it mean to truncate it early? We'll talk about those in the upcoming slides. IDE start is a message that's used to kind of trigger the use of keys. So the idea we talked about earlier, how there's a key exchange protocol and the two sides agree on what the keys to use. Once this configuration agent has set up the keys on both sides, it can trigger the transmitter to say, okay, it's time to start using the new keys. But somehow the receiver needs to know when the switch has happened. So the transmitter sends the IDE start message. And after this message has been sent, all subsequent protocol flights will be protected with the new key on the transmit side. And the receiver, when the receiver receives the IDE start message, it knows that, okay, anything that's going to come after this is going to be protected with the new key. So this allows the receiver to know precisely and keep in sync with the transmitter. IDE idle is a message that's sent really like a NOAA. And it's needed in some cases really to ensure, right, the sync that started up with the IDE start remains and the RX and TX remain in sync in various cases. I'll kind of give an example of how IDE idle gets used when we talk about the truncated MAC later. Let's look a little bit into the cryptography that's involved. So the underlying crypto is AES-TCM. And when you look at AES-TCM, this definition, there's sort of two components or elements of this. There are cryptographic keys that are used to protect the messages, and there's an initialization vector. Now, the keys, if you look at the diagram on the right, there's a key that's used by the transmitter, let's say the TX upstream, these green keys. The transmitter will encrypt the data and integrity protect it and sends it across the link. The receiver must now have the same key to be able to decrypt and check the integrity of the transmission. So TX upstream and the RX downstream, in this direction, both of them should have the same green keys. Now, in the other direction, from TX downstream to the receiver on the other side, there will be other keys, a different set of keys, these yellow keys, and the TX downstream and the RX upstream in that direction need to agree on and have this key. And these keys, the keys are established using the SPDM session we talked about earlier, and the key refresh protocol using the IDE start allows the keys to be refreshed without any loss of data. So you'll be using the old key and then you send the IDE start message. At that point, both the receiver and transmitter can switch to using the new key. So that's one aspect of one element of the AES-TCM. The second element of the AES-TCM is the initialization vector. You have deterministic construction. This initialization vector is 96 bits wide, and as shown in the diagram here, there is a specification-defined format for the initialization vector, and the lower 64 bits of this IV is a monotonic counter. And the idea is that the transmitter, so the initialization vector needs to get updated every time the MAC or the integrity value is sent across. So this monotonic counter gets updated by the transmitter every time it transmits a MAC, and the receiver, when it receives the MAC, would update the monotonic counter. So this allows the receiver and the transmitter to stay in sync. The initial value of this initialization vector IV is set up during the key exchange protocol. So you start up with the same value, and then every time things get transmitted, the counter gets updated, so the two sides stay in sync. This means this initialization vector doesn't need to be transmitted across the link. Just by the ordering of the protocol flights across the link, you guarantee that the two sides can stay in sync, and that saves bandwidth because you're not sending additional 96 bits over the link. Okay, let's look a little bit more into how the underlying crypto operates here, and how the components of the flit get mapped into the GCM elements. So in case of CXL.cache, the integrity value or the MAC is accumulated across multiple flits. And the set of flits over which the MAC is accumulated is called a MAC epoch. And this MAC epoch is defined by a number of flits, right? This is the aggregation flit count, which defines how many flits are in a MAC epoch. There are two modes of operation, and these modes determine what the aggregation flit count would be. So in case of the two modes of operation is the containment mode and skid mode. In case of containment mode, the idea is that the receiver must receive all the flits, must receive the MAC, check the MAC before any of the data or the opcodes in the flit are released for further processing. And what that means is now the receiver is going to buffer these, waiting for the MAC to be verified. So in the case of containment mode, the aggregation flit count is set to 5. It sort of gives us a good balance between how much bandwidth overhead is needed for transmitting the MAC and what the latency and overhead and buffering requirements are on the receiver side that's going to wait for the MAC to show up. And since the flits are never released till the MAC verifies, this mode kind of gives you the best security. The second mode, called skid mode, here the aggregation flit count is much larger. It's 128 flits, which greatly reduces the bandwidth overhead because the MAC is only sent now every 128 flits as opposed to every 5 flits. In skid mode, the receiver is allowed, right? They don't need to buffer up everything. The receiver is allowed to release this data for further processing without waiting for the MAC. This means that the skid mode has much lower latency, but since this data is released and consumed prior to the MAC check, there's this risk, right? That some of the, there's any threat that results in flit data modification that's later detected by MAC check. It may be too late, the data has already been consumed. So this requires a careful assessment at the solution stack level to understand the trade-offs and the value, the lower latency and lower bandwidth overhead would bring. The diagram in the bottom here kind of shows how the elements of flit get mapped into the components that NIST defines for ASTCM. So there's two parts of the input to ASTCM. There is the additional authentication data. This is the information that needs integrity protection but is not encrypted. And then there's plain text, which is both encrypted and integrity protected. So look at this example, see, the very first flit on the left, it's a header flit. So the flit header with 32 bits is mapped onto the AD, which is only integrity protected, and the rest of the flit content is mapped onto plain text because it needs both encryption and integrity protection. Flit 3, if you see, is exactly the same. It has a flit header and it has flit contents. Flit 4 is more interesting. It's an all data flit. So the entire flit, there's no header. So all the 64 bytes of this flit is going to be encrypted and integrity protected. So it gets mapped onto the plain text portion of ASTCM. Now, flit 2 is interesting. It has a header, and this header carries, the header slot carries a MAC. This MAC is really for the previous MAC, but it's really for the flits that are not shown here, right there on the left of the diagram. And logically, this MAC belongs to those flits, but it's transmitted later. And since this is part of the previous epoch, it is neither encrypted nor integrity protected in this epoch. The MAC for the flits in this epoch, the ones that are shown in this screen, would actually come later, right to the right at some point. This diagram also shows kind of how the AES robustness feature works, but we'll talk about that more later. Okay, when you look at sending back-to-back traffic, this is the case where there's continuous stream of flits, and it's advantageous to use the MAC slot to send the MAC. First requirement, of course, is you have all the flits in the MAC epoch, and then the MAC for this epoch will follow after that. And the order in which the MACs are received should be sort of same as the order in which the epochs are sent. So you send the MAC for epoch 1 first, and then you send the MAC for the epoch 2. Generally, the requirement is, as soon as you send the flit for a MAC epoch, the MAC for that epoch should follow immediately. But it may take a little time for the transmitter to compute the MAC. In this example, the flits in MAC epoch 1 are encrypted, they're processed, and then it takes 1 flit time for the MAC to be ready. But we don't want to introduce any bubbles in the transmit pipe, so the flit for MAC epoch 2, flit 0 of MAC epoch 2 is parallelly sent on the link while the MAC for the previous epoch is getting ready. So, and then the MAC is ready at the, in parallel with flit 0, and then it gets transmitted as part of the header in flit 1. So this is sort of the example that's shown in kind of the figure in A. Now, when you look at the case shown in figure B, what it's showing is, okay, the MAC got ready exactly the same way as before. So flit 0 of epoch 2 was transmitted. In parallel, the MAC was getting ready and is ready at that point. But in flit 0 of MAC epoch 2, there was a multi-data header. So when there's an empty edge there, it takes the subsequent flit would all become all data flits. So there could be up to 4 all data flits, which means this MAC, even though it's ready, the yellow MAC cannot go out of the link till flit 5 of the epoch 2. And at that point, it gets sent as part of the header slot. So this means that the MAC could get delayed, beyond even like 1 flit or whatever. So in order to minimize how long the receiver has to wait, the spec defines a limit. So the latest a transmitter could send a MAC for an epoch would be the 6th flit after the epoch ends. Let's talk about TMAG Flight that I had alluded to earlier. This comes up in cases where the traffic is not continuous. For example, let's say the link is going idle and it's a containment case, so 1 flit was sent on the link and the link is going to go idle. So the receiver has received this 1 flit, but they don't have the MAC, so they don't want to wait the receiver to wait indefinitely. So the spec defines a mechanism called a way to terminate the MAC epoch early and say, okay, and I sent you 1 flit, but I'm not going to wait for 5 flits or 128 flits. I'm going to send the MAC right now. And this will allow the transmission of the MAC with even though fewer than aggregation flit count number of flits have been sent. And this is done by sending what's called the IDE control flit, the TMAG flit. Once the transmitter has decided it's going to terminate the MAC epoch early, it has to first send the TMAG flit. And before it can send any new protocol flits that would really belong to the next MAC epoch, so it can't get into leave between the epoch 1 flits and the MAC flit. In a typical implementation, when you're doing crypto at this high speed, it's typically pipeline rate. You're trying to do a full line rate throughput, let's say, of 64 gigabytes per second with a by 16 link. So in these cases, the crypto engines are typically pipeline. And it's possible with the AES-DCM to pre-compute the crypto output that would then minimize the encryption decryption latency. But when a MAC epoch is terminated early, the receiver will need some time to kind of clear out any pre-computes it has so it can get ready for the flits that belong to the next MAC epoch. So this amount, how long it takes the receiver, is a configurable, discoverable parameter from the receiver. And it gets configured into the transmitter as truncation delay. And the transmitter really must wait for this amount of flits. And this wait is, generally filled with an IDE idle flit so that the receiver can get ready to receive protocol flits to the next packet. Let's look at how encrypted plaintext CRC that I alluded to earlier gets used. So this is a mechanism to provide robustness of crypto engines, right, to improve protection against hard or soft errors that are internal to the crypto engines. This is integrated into the back check mechanism. And if you look at the diagram on the left, it's how the transmitter would, it's sort of what the transmitter would do. So it has the plain text content, generates a CRC on it, this is the plain text CRC, and the CRC gets appended with the plain text. So I have the plain text and its corresponding CRC, the whole thing gets encrypted, and the ciphertext along with the encrypted plaintext CRC is used to compute the map. So all of this is now ready to go out. In the case of CXL.io, you would actually send the ciphertext and send the encrypted plaintext CRC so the receiver receives it. In the case of CXL.cache and IDE, there are really no bits to send the encrypted plaintext CRC. So from a protocol perspective, these bits cannot be sent. And it also turns out that if you don't send the encrypted plaintext CRC, you actually save on the bandwidth because you're not sending the two additional bits on the link. Now, this means because the encrypted plaintext CRC is not sent across the link, the receiver now needs to do some additional work. Right? The receiver receives the ciphertext, it has to decrypt, generate the plaintext, compute the CRC on it, and then re-encrypt that CRC so it gets fed into the MAC calculation that gets verified. It turns out, right, in AES-TCM, it's really, an XOR with the AES counter output. That's how encrypt decrypt works in AES-TCM. So this means the receiver side is sort of, comes down to doing two additional XORs in the path to MAC computation. So it's not really onerous, while it avoids the needing to transmit these bits on the link. Okay, let's move forward, talk a little bit about how the link errors are handled. So the baseline set of error, link error handling. The link CRC protects against any transient errors that happen on the link, things that could be due to electrical or other reasons. And there's a retry mechanism built on top of this CRC that would retry the flight in case a CRC error was detected. IDE has no impact to either the link CRC because the link CRC is not protected by IDE in any way, and not on the link retry mechanism. So from an IDE perspective, these things happen independently as they do, with or without IDE, and IDE only sees flits that have passed those CRC checks, so that are kind of notionally good that came on the link. IDE itself, of course, introduces its own set of errors, right? So anytime you have let's say an integrity error that was, let's say, due to a thread that flipped the bits on the link, there will be a MAC error that's discovered by the receiver. As we talked about earlier, IDE accumulates the MAC across multiple flits. So when the error is discovered, it's not clear, right? You cannot deterministically know where the error happened, which flit was it, was it in data or header. So all of the accumulated flits would be dropped and an error would be logged. So once this error is logged, all subsequent IDE traffic would also be dropped till the link gets reset. In case of a device that has some state, right, there's a couple of ways to do it. You may have some cryptographic state, that's pre-computed, or there may be plain text data sitting around. And there are a couple of strategies, right? This could either just be cleared, or these could be, access control so that they don't leak out. And from a link reset perspective, let's say the link is reset either because of an integrity error on the IDE, or in case just the link gets reset, all of the secrets in the device and all of the IDE keys get reset. And then there's a need to kind of go back, start over again, and do the full device authentication, key exchange to reestablish the IDE connection. So today we reviewed the capabilities that CXL, what CXL offers in terms of security, talked about how device attestation works and how you know who's on the other side and the mechanisms that are needed to do the key exchange, right? This uses the CXL IO interface and is sort of built on top of the SPDM and DOE mailboxes. We talked about how CXL IO protocol, the IDE for it follows the PCI ECN, and looked at some of the properties of CXL IO IDE. We dug into the details of CXL.cache and IDE, right? Really, the detailed definition that's in the 2.0 specification. We talked about sort of the two modes of MAC transmission, the containment mode and skid mode, and how the IDE is implemented in a efficient manner, right, to get the link integrity and confidentiality that's low bandwidth and that has low latency impact. And we also talked about the use of encrypted plaintext CRC for providing crypto engine robustness. So thank you all for listening, and over to you, Uza.
Thank you, Raghu. We will now begin the Q&A portion of the webinar, so please share your questions in the question box. We can start with the first question. In the figure on slide 11, if a key switch exchange process happened between the MAC epoch and the MAC epoch 1 and the MAC epoch 2, when exactly will the IV counter be configured at each TX-RX port? Is the RX side still using the old IV value to decrypt the first flit of the MAC epoch 2?
So when we look back at this definition of AES-TCM, all of the flits in a MAC epoch really have to be processed together. And that would mean there's one key, one IV for all the flits in the MAC epoch. And I would say that the key switch really has to happen at the boundaries of MAC epoch. So all the yellow flits would use one key and one IV, and the green flits would use a different key and different IV. But realize that the MAC, the MAC for the yellow flits, even though it's coming later, would have been processed with the IV and the key from sort of the previous epoch. So one kind of way to kind of address some of these would actually be to do a truncated MAC and end the MAC epoch early before switching to the new key. Let's see.
Okay. Is there an impact on latency of CXL.mem read and write commands?
With the latency impact would depend on the mode of IDE that's used. Like we talked about, there are sort of two modes of aggregation. There is a containment mode and skid mode. When skid mode is used, there's no latency impact because as soon as the flit is received, it's decrypted and sent forward, so the latency will be minimal. In containment mode, of course, the flits are held back till the MAC check completes. So there would be an additional latency because the flits have to arrive, the MAC has to arrive, and all this has to be checked out. Good question. Let's see. The next one. Could you please?
You know, the keys on the fly question actually goes along with the epic question, I think. Maybe speak to that one.
Sure, I'm trying to find it. But yeah,
At the
what was
bottom.
the other
So
question?
when keys are changed on the fly, then what will be MAC calculated on?
Yeah, like I said earlier, the MAC is always based on the keys and IV that was used to protect the flits in the network. So if you look at how ASTCM defines the mapping, like you can't take all of the flit content that gets mapped into AAD or into plain text, and this is processed with a key and an IV to generate the MAC. So this whole unit goes together as one. The key switch happens, the new flits will get encrypted with the new keys, they'll be integrity protected with the new keys. Hope that's clear. More questions, let's see. Are there requirements to distinguish IDE-related link resets from non-IDE or implementation specific? In general, I think I'd say that any reset, when there's IDE enabled and getting used, when the link gets reset, any of the secrets that were there from the previous, reset epoch, so to speak, has to be protected. Like, when you come back after reset, it's not guaranteed you're talking to the same person. So the IDE keys will get cleared, and any of the plain text or crypto state will also have to get cleared. Does the traffic require to be back-to-back? If it's sequential traffic, how is IDE expected to behave? I think so. It doesn't need to be back-to-back. There can be, bursts of traffic. So you could send, into this example that I have on the screen, you could send flit 1, and then maybe some amount of time before flit 2 arrives or flit 3. The flits are clearly ordered at the link level, so they get in that order, and the receiver sees in the same order that the transmitter sent. But there may be practical reasons, like if the link is getting idle for a very long time, then maybe need to terminate the MAC epoch early and send a TMAG so that in containment mode you don't have very large latencies.
Raghu, do you want me to take this one about
I was
why is
hoping you would, there. Please.
Yeah, why is selective stream not supported in CXL.cache? Yeah, so the key observation here is that in PCI Express, the TLP, the transaction layer packet, which is the routable unit, is the basis for IDE. And so, setting aggregation aside for the moment, the connection end-to-end between two ports implementing selective IDE is, I'm sort of making air quotes, it's simple because you take the entire unit that comes into the switch, determine which port it goes out, and pass it out. Now, this figure here actually illustrates nicely how CXL, of course, has a very different structure, where in general you're going to be applying the MAC across a relatively large number of flits that are potentially all routing to different places. And this essentially precludes having a selective IDE mechanism applied to this. And if you turn that around and say, what if you applied the MAC to each individual flit? Well, it would be a very significant impact on the usable bandwidth, right? So it's not a desirable place to land. So essentially, this is something that falls out of the natural difference between a flit-based protocol like CXL.cache and a larger, packetized protocol like PCI Express, which of course then applies to CXL.io as well.
While you are there, would you want to talk also about the eDPC link reset? What does it mean? Does it mean we need to restore CXL.cache IDE after an eDPC link reset on CXL.io?
I think that sorry, actually, I'm trying to find the question. In general, the IDE connections on CXL.io and CXL.cache.mem are managed independently of each other. And the reset cases, of which there are many, I think require some thoughtful treatment in a platform and application-specific way. But as a general statement, they're not really tied to one another per se. Now, obviously, there are some things about the configuration of the connection that are established over CXL.io that, if they are changed, probably in turn impact the cache-mem connection. So I think that, well, that's probably all that I can say without a whiteboard. Raghu, I mean,
No, I guess I was going to say that, in many cases, when you start doing downport containment, it would also mean that the link is going down or the device is getting unplugged somehow, which would mean that the entire device is going away. It's not the IO link or the cache mem link. I mean, if it was in a system, like you said, if it was carefully thought out and only one side is going down, it may be possible to keep the other one alive. But
yeah, and
normally, if you treat CXL.io IDE and CXL cache-mem IDE as sort of two parallel, independent entities. Sorry, go
yeah, I
ahead.
think that's the overarching concept, that really these things are independent at the level of the protocol, which doesn't mean they're independent at the level of some higher application concept, but those are implementations or scenario specific, if you will. And there's an overarching, philosophy here with IDE, which is IDE is just protecting the connection, right? It's necessary to have appropriate security policies at both ends of this connection. And so, again, as a very general statement, right, it's simply a requirement of use that if the security properties of, say, the .io connection change in a certain way, and that impacts the security posture on the cache-mem connection, then the device or the host needs to ensure that that's enforced. But that's sort of outside the scope of IDE per se.
Right. So it's going to take the monotonic counter question, maybe, just so that it's clearer what I was talking about. Find the slide. If I can. Okay, so the monotonic counter is used as part of the IB construction. So when you look at ASTCM, the IB is updated every time a MAC is transmitted. So, and this means, right, when the transmitter, encrypts and computes a MAC, it's using the keys and a particular value of the IB. And then the receiver, of course, has the same key, but it also needs to align to the same value of IB. Otherwise, the decryption will come out incorrect and the integrity verification will fail. So the use of the monotonic counter is, let's say both sides start at 1. Okay. At key establishment time, both of them have it as 1. Every time the transmitter sends, let's say, 5 flits and sends a MAC, the receiver sees the 5 flits, it sees the MAC. For the next MAC effect, the transmitter is updated the monotonic counter to 2. The receiver, having seen the flits of the first epoch, can now update itself to 2. So that way, the two sides will always stay in sync. And so that's sort of the general use of the IB. And the advantage of a counter is that it's fairly straightforward to keep the two sides in sync without having to send it across the link. Let's see. Is it possible for a device using CXL.mem or CXL cache to optionally participate with the security protocol? The CXL cache and mem are both coherency protocols, and they're covered by the cache-mem IDE. So a given slit, if you think about it, would have some cache transactions or some mem transactions, assuming the device is supporting both of those, like it's a type 2 device, for example. So in that case, no, it's not possible to separate those out independently. But if the device was just purely a type 3 device, it could then say, I only need to implement .mem protocol, and that would get protected by IDE.
I think maybe there's also a good segue to the is IDE optional question.
Yeah, I was going to go to that. Thanks. Go ahead, Dave.
Yeah, well, I was going to say, just to expand on what Raghu just said. So CXL.io has its IDE capability. CXL.cache.mem has its IDE capability. They're both effectively and independently. Anyway, they're both optional. But obviously, if an application requires security of the kind that IDE provides, then that application can't meaningfully work without IDE being supported on both sides and turned on, right? And again, this gets back to the idea that both the device and the host are required to enforce a security policy that's appropriate for whatever they're doing, where that's somewhat application specific. But so, for example, a device that requires IDE for secure operation would be obligated to determine that IDE is not only supported, but is in fact enabled and operating before it enters into any sort of secure operational mode. And of course, if IDE were to go down, then it would disable that secure operational mode. And this is essentially an upper level protocol requirement.
Yeah, I'm going to take this question on slide 3. Okay, we can go back to slide 3. Will a switch have to interleave GCM streams with different keys from and to each point? Or is it programmed once and static? It would depend on sort of the protocol, right? CXL IDE has the ability to have multiple streams. So and you have stream IDE in CXL. So data belonging to different streams or TLPs belonging to different streams are protected by different keys. And the switch, it would naturally flow through the switch in an interleave fashion. But the switch would not really be doing anything special there. But when we are doing CXL.cache.mem, it's a link level protocol. So there is a link IDE going from the root port to the switch, and then from the switch to the endpoint. And those would be, there's one set of keys between the root port and the switch. There's a different set of keys between the switch and the endpoint. And all the flits, all the cache.mem flit would all be protected by the corresponding IDE keys. Let's see, is there a debug mode for CXL and PCIe LAI to handle IDE? Dave, would you like to take a shot at that?
Sure. So this is, so first of all, I assume we're talking about LAI, like as in with a logic analyzer or exerciser type test equipment. And this is something that is essentially outside the scope of the PCIe and CXL IDE definitions themselves, but we are actually working on a proposal for, essentially a uniform way of handling this, where, of course, the thing that's difficult here is that test equipment would typically trigger on information that in this case is now actually going to be encrypted. And so even just to display, of course, what's going on the link, it's necessary to be able to decrypt packets, which means being able to agree on the key, either because you have perhaps a set of agreed upon keys that's arranged in advance that are specifically for debug, or because you have a mechanism to essentially leak the key to the test equipment. Now that can be done offline. There's a more difficult problem, which is, again, if you want to trigger on information that's encrypted, then of course that processing has to be done real time or close to real time. But that is something that is being worked on.
Let's see, I'm going to take the first one here. In skid mode, it seems that protocol flights are released for further processing without waiting for the MAC. While this might be good for latency and bandwidth, how does it work if the MAC is found to be incorrect? Does this not increase security risk due to the lag in the MAC check? So I agree with the observation completely, right? Yes, there is an additional security risk, and that needs to be carefully weighed against the benefits. And in fact, the threat model, that's under consideration as well. Like, what is the specific types of threats that a particular usage is concerned about, and what are the benefits of the additional latency and bandwidth that will be obtained. So yes, it does require careful analysis and thought. Any other thoughts, Dave, on that?
No, I think that covers it.
Okay. Let's see. Can you specify what is expected from IDE firmware implemented outside of CXL IP? That is, what is negotiated on the mailbox of CXL IO? Where is the definition of the key exchange and agreeing on starting counter? So there is an ECN for the CXL.cache mem protocol, which discusses the key establishment protocol. For the CXL IO, the use of DOE mailbox and how the keys are negotiated are covered in the PCI IDE ECN itself. And so, yeah, I mean, so we walked through the device attestation and key exchange flow, and I would expect sort of the, some kind of an IDE firmware or a device security manager to be involved in that negotiation and agreeing of the keys before they get programmed into the crypto engines themselves and a part of the CXL IP.
Yeah, and it's probably worth mentioning as well that PCIe IDE established a key management protocol, which is kind of the starting point. Then in CXL, I believe the capabilities of that are somewhat expanded, and then the idea is that we would continue to evolve both the PCIe one and the CXL one in this kind of a step back and forth fashion, so that they're essentially at the same level of capability. But I do anticipate that both of them are going to grow some additional capabilities beyond what was defined in the initial key management protocol.
We take this one. Could you please refer to MLD, CXL.mem devices serving multiple servers? I think the question is, how would IDE work with a MLD device? So nominally, right, I mean, the way I view an MLD device is that there are two hosts or multiple hosts connected to it, and if IDE is required, there would be an IDE connection from each host to this device. So that would be one mechanism where the device is directly connected to multiple hosts, and each one, it would have multiple links, one going to each server, and you would have an independent IDE with each one. Clearly, the device, of course, would have to further understand sort of the implications at the usage model level, at the overall system level of what it means to have all these different servers sharing the same link and the same device, and what if some of them are enabling IDE and others not, sort of the underlying implications of how do you guarantee the security properties that the usage model requires. So that would be some considerable thought that has to go into building such an MLD device. A second option for an MLD device would be that there would be a switch in the middle, that the switch should actually be the one that's multi-headed, talking to different servers. In this case, of course, again, there may only be one IDE link, but it may be servicing information from, so the switch is sending the data from multiple hosts to one endpoint. And again, in this case, the device has to carefully weigh and understand the implications at the system level of how things are getting shared.
Hey, being mindful of the time here, we will wrap up today's webinar. So thank you, Raghu and David, for sharing your expertise. We couldn't address all the questions we received today, but we will be addressing them in a future blog. So please follow the CXL Consortium on Twitter and LinkedIn for updates. The presentation recording will be available to watch on demand on the CXL Consortium's YouTube channel, and the slides will be available on the CXL Consortium website. If you would like to learn more about CXL, please join the CXL Consortium and download the evaluation copy of the CXL 2.0 specification and engage with us on Twitter, LinkedIn, and YouTube. Once again, we would like to thank you for attending CXL Consortium CXL Link Level Integrity and Data Encryption webinar. Thank you.